Thanks for the introduction, and I have to start by disagreeing with the definition of what NIPS is. It's not the main conference for deep learning, it's the main conference for machine learning, and I present more or less the other half of the NIPS community. Talking about the other ways of building models that are not deep learning, even though my talk will of course converge to more or less the same direction. So what I'm talking about today is probabilistic programming. And here's a quote from a famous researcher in Helsinki area about what does it mean. So it is the same thing to probabilistic modeling as deep learning is to neural networks. So neural networks have been around for ages. Probabilistic modeling has been around for ages. Deep learning came and changed the field for neural networks, and probabilistic programming will do the same for probabilistic modeling. In particular, it will allow us to easily build probabilistic models by composing them from smaller parts, which has always been the idea, but hasn't been very practical in the past. And it also is kind of a framework for building the tools that will make our life easier. So just to start with probabilistic models. I'm actually sure that practically all of you have seen a lot of probabilistic models. It's just an umbrella term for any model that we describe by specifying probabilities. We're trying to kind of explain how we think that the data might have been generated. And we assume that there are some unknown parameters, and we postulate that they are random variables that come from certain probability distributions. So I just listed here a very short list of examples that all fall under the very same basic principle. So hidden Markov models, practically all regression models, hierarchical regression models, mixture models, in fact, majority of deep learning as well. So all the neural network structures are, in principle, they are special instances of probabilistic models. I'll get back to that later, that what's the actual difference. As a concrete example, so here's a model that you might have heard of, which is called latent Dirichlet allocation. It's a model for natural language text. A collection of text documents. I will not go to the details. The important things to remember is that there can be a graphical representation. So these are often called probabilistic graphical models, where the graphical representation describes what kind of a story we assume. And on the left, we have a collection of probability distributions that define the actual model. So this is the so-called topic model, which just assumes that we're generating documents by saying that they consist of a certain set of topics, and then we are creating that the individual words are kind of coming from those topics. No need to go to the details, and I will not go to any more details than that during the rest of the talk either. Some terminology. I assume that most of you are actually more or less familiar with this. But this is the standard way we propose and talk about these models. We first assume that we have a model that has parameters. We don't know those parameters, but we can say something about them. We can say that these parameters should be positive, or we can say that we think that an average height of a human being is around 0.7 meters. Around that, we don't know what it is actually. Then we have the likelihood, that is our actual model. That what is the probability of having seen this particular data given certain values for the parameters. And what inference for probabilistic models is all about is application of a very simple standard rules of probability that has been given a fancy name of Bayes rule. But it simply is the equation that tells us that after seeing some data, what do we now know about the parameters of our model? And that's called the posterior distribution. It's computed by this very innocent looking equation. it's not quite as innocent as it looks like. I'll get back to that later again. And once we know that there is some distribution over the parameters, when we want to use the model for something, we're going to make predictions. What kind of a data point we believe that the model could produce, and what we should be doing is that we should be integrating over the distribution that characterize what the parameters could have been. And you might start asking the question of why would we ever want to do this? So I said that the likelihood describes how likely is this data set given a certain set of parameters. Why don't we just maximize our likelihood with respect to the parameters? And the answer is yes, you can do that. That's actually what most of the deep learning success stories nowadays do. You formulate the loss of your network as the likelihood of the data given the parameters. The parameters are the network weights. And then you just start optimizing, which is fine as long as you have a lot of data. The distribution, there's not much uncertainty about the parameters remaining if you have, well, at the limit of infinite amount of data, you will know the parameters. But that's not nearly all of the interesting applications. So there's a thing that could be called parameter inference. So for a lot of instances, we don't want to just say, what's the object in this image, but we actually have a physical model of some kind, or a model of human behavior or something. And we're interested in figuring out what are the actual parameters. What's the Planck constant? We can observe some data, we can build a model, and what we want to really know is, what do we know about these particular parameters? There's another argument which is related to quantification of uncertainty. So when you don't have infinite amount of data, the data will only determine the parameters up to some accuracy. We would want to know to what accuracy. And when we make the predictions, we would want to average over this uncertainty. And I'll make a claim that, I mean, even in majority of the big data applications, for the interesting questions, you don't have enough data. Talk about medicine. We can record data about millions or billions of people and learn models of the generic behavior. Then when we want to make predictions for you, you don't want to take 1,000 medical examinations. That would be enough to figure out what's happening in your body. Related to the quantification of uncertainty is that especially if we want to build automatic systems that actually make decisions, or we don't want them to make them kind of in an ad hoc manner, but we want the system should know how certain it is about the decision that it's going to make. So here's an example, a simple example about the parameter inference. It's simple because I did it this morning. So I started from scratch. So I wanted to answer the question of, have I been exercising more recently? So I was surprised. I was actually able to download from my phone the health data that it gathers. I just said, please download, and it gave me 180 gigabyte XML file. But it did have the raw data that it records about my calorie consumption and steps and whatever. And then I looked at 2 consecutive months, and I want to find whether I have been exercising more in October than I did in September. So this is a real parameter inference question. I want to know this quantity. I don't want to predict how much I will exercise in November, or I really want to know, was there a change? And if I just look at the mean value, so what it records is the amount of calories that I consume above the basic metabolism for a person of my weight. And these are the averages. So there's an increase of around 30 kilocalories per day. And the question is, did it go up? Based on this, you don't really know. What you could do is run a statistical test, a t-test. It will give you a p-value of, I did try it, I don't remember the value, something close to 0.05, so maybe it did. So what I can do is that I can build a model. I say that there is for September, my average consumption was at certain level, and the individual days are random fluctuations around that. And I do the same for October, and then I ask the question, are the rates different? So the standard t-test procedure. And here's the result. This is the result that we want to be looking at. X-axis is how much did basic rate go up. And this is a density plot of giving the probabilities. In particular, we see that there is around 13% probability on the left-hand side of 0, meaning that maybe I actually, on average, was less likely to exercise, even though the average calorie consumption did go up. So under the model, this is everything we can say about the 30 days of data that we have. It's not enough to determine for sure that I did exercise more. Perhaps more importantly, this is conditional on the model I built. Then I took a look at the data. I assumed here that my individual data points come from a normal distribution around this mean parameter. I noticed that there are some days when I really went for a 2-hour jog, which showed that the mean values increased a lot because of those, but maybe the average rate is not so much. I can take that into account by making a one-line change in my code for doing this analysis. I say that my observations come from a t-distribution that has heavier tails, and the result changes. Now I have a 24% probability of believing that I actually didn't really exercise more. I just happened to have individual days during that month where I had a high consumption for some reason. And this is what we want to do. We want to know about the parameters, and in a justified way. Here's a bit more interesting example I picked from ICML, the other main conference in our field. A real natural science question being addressed by these kind of models. So you take images of the sky and you want to actually count how many galaxies there are and how many stars there are in the universe. No way of ever obtaining ground truth for that. We just want to learn that. And what they do is that they build a certain type of a model where the parameters are the properties of the galaxies. What kind of a galaxy there is and whether there is a galaxy. And then they do inference over this. So this is the kind of applications we're looking at instead of the classical classification problems. And the challenge. So I started by saying that there's this innocent looking Bayes rule that tells you how to do this. The only difficulty is that below the line in the Bayes rule, we have this thing called evidence or the marginal likelihood, which is the probability of the data averaged over all possible parameter values. In a typical model, we might have hundreds, thousands, or millions of parameters, so it's an integral of extremely high dimensionality, yet we need to do something about it to actually find the true distribution as the solution. I skipped all the details. So this is what Bayesian inference has always been about. Building algorithms for tackling with this challenge. So there's Markov chain Monte Carlo, so these called sampling methods. There's variational approximations, there's expectation propagation. In fact, there's 20, 30 years of research in machine learning and statistics that is purely about how do we do inference for a specific family model or a specific family of models, like the latent Dirichlet allocation, or a mixture model, or a hidden Markov model. This is what it looks like. So this is taken from Wikipedia, from one of the simplest models you can think of, latent Dirichlet allocation. It starts by looking at, we look at this probability. It can be simplified as, and then comes a couple of lines of equations, and then it continues. This can be further simplified by leveraging the property of gamma function and so on. So it's a derivation of this kind, usually takes a couple of pages in an appendix in a research publication and so on. For one single model, we need to do this. That's fine. The bigger issue is if we change the model a bit. I say that I'm not happy with this normal distribution assumption that I made earlier, I want to plug in t-distribution here in my model. You need to do the same again, most of it. So you'll get a research paper out of it, but I mean, science is progressing very, very slowly. And always, I cannot try easily a small change because it takes me a couple of months to do this. So what we should be doing instead is, there's two conceptual things, writing the model and doing inference. They should be separate. And this is pretty much what happened with deep learning. We don't worry about things like computing the backpropagated gradients, or we don't worry about the details of an optimizing algorithm. We instead just build these fancy layered structures out of small modules. And it's going to happen the same thing for Bayesian modeling. I'm sure of this. The problem is harder. So we are behind. It's not happening yet. So there's a small anecdote. So I actually started my career 15 years ago. The first thing I did was I did derive on pen and paper the backpropagation gradients for a certain type of an MLP, took up MATLAB, coded it up and everything. Now it would be 5 lines of code, more or less. I could do it in 10 minutes, thing that I did for one summer. Around 5 years ago, I was doing these variational approximation for certain types of probabilistic models, implement 15 pages of integrals and then writing them down in R and Python. That nowadays would be 10 lines of code, or at least should be. We're maybe not quite there yet. Okay, so probabilistic programming is what's going to make this happen, or to some extent has already done. Here is the latent Dirichlet allocation model I started with as an example, written in Stan. That is one particular probabilistic programming language, maybe the most mature one of those. This is the whole code. And the code is actually exactly the same thing I wrote in mathematics, the mathematical equations on the one of the first slides. Very tiny details, but rather than that, this is the code. Then we just say, please do inference. Okay, so what's under the hood? I said that we've been spending decades building Markov chain Monte Carlo variational approximations and so on. That's still what's happening. This mathematical principle of how we can do inference. But there's a lot of technical changes because the field has been progressing, and maybe the most critical one is here that we've switched to algorithms that can use gradients, in particular automatically computed differentials of the logarithmic probability, and we now know how to use those as part of a MCMC algorithm or as part of a variational approximation. So it's pretty much the same thing that made deep learning easy. We now have a tool that can compute the gradient of a complex model automatically, and then we know how to use those gradients as part of the learning problem. It's still harder. I mean, we're still not just optimizing for the likelihood with gradients. There's a lot of mathematical details of what has to be done, but it can be put behind the curtains and it can be implemented in an automatic software. So what did we gain? So if we started with, okay, we know how to write the model and then we do the inference by hand. We can now do it for a wide set of models fairly automatically. And I think the main gain is that we gain flexibility. The automatic tools are not as efficient, not as robust, not as accurate as the hand-tuned things that we've been building for 20 years. But we can make these small changes and run the code again and see what comes out. We can also do fancy things like having a model that actually has while loops or other these complex kind of structures, as long as we can compute derivatives of this part of the model. There's also examples where part of your model is like, okay, I define a physical structure, then I take Blender, I render an image out of that, and so on, where you try to still do inference over the shape of the object based on that. And if you want to do this now, today, then I say that STAN is the tool. That's the most mature tool for probabilistic programming. It uses Hamiltonian Monte Carlo for doing the inference, so that's easy to start with. That's what I used to create my small example in 5 minutes, more or less. So it took longer time to plot the figure than it did to run the model. What's still missing? So this is pretty much my piece of news where I was also in NIPS, and what's happening there is that this is what we're working on. The gradient-based algorithms for doing Bayesian inference are nice and fancy. They're easy to use, but they are nowhere near being the final solution. We know that for any given problem, we can do better inference. We can have dynamic programming algorithms and stuff like that. And we just need to learn how to combine those with the gradient-based learning algorithms to make the models work just as well as the hand-tuned ones for the models for which that is easy. There's a bit of a scalability issue as well still. So we're doing gradient-based optimization as in deep learning, but it's a more complex optimization algorithm. So that we still need to work on that, especially the MCMC algorithms they're accurate but slow. The other techniques are faster, almost as fast as maximum likelihood, but they don't work yet for all models. Maybe for this audience, then I should say a few words still more about the connection with the deep learning. So pretty much all the deep learning models are some sort of probabilistic models. The difference is just that whether we do full proper Bayesian inference, which we need to do if we're interested in parameter inference, or whether we just kind of want to find some reasonably good solution and go ahead with that. And another important aspect is that we are now using gradients, we are using automatic differentiation for computing those gradients, which means that we can build the tools on top of the same platforms. They're not ideal for building Bayesian inference algorithms, but people are working on that as well. So there's some examples that are actually built on top of TensorFlow or Theano. And I make a claim, I keep on making this claim that in a couple of years, there's no difference between the software tools. It's the same interface. It's the same way of defining the model. Which inference algorithm you use, that will then depend on what you want to do. If you want to recognize the actual galaxies, you need to do full Bayesian inference. If you want to build yet another image classifier, you'll just use maximum likelihood and be happy with that. Hopefully the software will also determine that automatically. Here's an example of one of those tools. This is from the NIPS. How you actually create simple deep learning models as well using these probabilistic programming tools. So variational autoencoders, the simplest possible probabilistic model you can do this way. So I'll just finish here. I think I've spent my time already just to say that there's academic stuff happening around probabilistic programming in Helsinki. So I'm at University of Helsinki. I have a reasonable sized project where I'm working on the variational approximations funded by Tekes and a couple of companies. I see some people in the audience from those. Aki Vehtari from Aalto University is part of the STAN development team. It's led from New York, but he's part of the team officially. He's looking in particular ways of assessing of whether the model is good or not. There's some research activity at Aalto and University of Helsinki about even more flexible things. So it should be ABC, not APD. So approximately Bayesian computation on how do you do the same thing if you don't even know how to specify your likelihood, but you have to have a simulator for that, like a simulator for some physical process. And yeah, I know some companies are actually using these tools. If you are one of those, but I don't know about it yet, I would like to hear. I'm interested in whether these tools are being used.
Hi. Do you have any success stories where this is used successfully? I've heard that Galaxy thing before, but do you have other examples?
Okay, so for Bayesian inference in general, that's pretty much everything that you've ever heard of that comes from machine learning. That is not kernel machines and it's not deep learning. For probabilistic programming, I think the main success stories right now are at applied statistics. So we're not talking about AI applications that revolutionize the world, but we are talking about an individual sociologist looking at a certain aspect and actually being able to build more complex model that helps them understand whatever the process that they are looking at. So I think that's right now, that's the main core, the target audience for STAN, which is the most mature tool. So I think that's the state of the art right now.
Hi, I have just a technical question. So how can you, or how you successfully treat discrete variables in this probabilistic programming or related models?
That's a very good question. So I showed the example of LDA being implemented in STAN, and what you actually do is that you analytically integrate out the discrete variables, which can be done, which means that you need to do a bit of math yourself. Just these NIPS, there were 2 papers that are, a month ago, 2 archive papers were published that let you do variational approximations with discrete variables. I don't know yet how efficiently. So that's particular challenge here with all of the models that rely on automatic differentiation. The hand-tuned algorithms often are specifically designed for the cases with discrete variables. So that's what I would kind of suspect is where we need those. We need to merge the hand-tuned local propagation algorithms that can handle discrete variables as part of a bigger model that uses derivatives for the rest. Okay, thanks.